All right, so we talked about target devices, so it is time to talk about performance metrics. In cryptographic algorithm design, there is a trade-off between performance and resources required for a given security level. So most of the time, our aim is to find a sweet spot between security and performance. Okay. Performance can be expressed in terms such as power and energy consumption, latency, and throughput. The resources required for a hardware implementation are usually summarized in gate area, gate equivalents, or logic blocks, also known as configurable logic blocks, logic elements, adaptive logic modules, or slices. Okay, so at the side of FPGAs or ASICs, these are the things that we are interested in. In software, this is reflected in number of register, RAM, and ROM usage, etc. So resource requirements are sometimes referred to as costs, as adding more gates or memory tends to increase the production cost of a device. So recall our last week's discussion. At the IoT side, sometimes you produce a very small device, maybe millions of times. So making it 1 cent cheaper actually profits you a lot. This is why you are trying to make it as small and as cheap as possible. That is the main idea. Power and energy consumption are relevant metrics due to the nature of many constrained devices. Power may be of particular importance in devices that harvest power from their surroundings. An example will be an RFID chip that uses the electromagnetic field transmitted by a reader to power its internal circuit. So this is what we do in most of our smart cards and so on. Energy consumption, in other words, power consumption over a certain time period, is especially important in better operated devices that have a fixed amount of stored energy, right? So, if you're charging your iPhone 5 times a day, you know what I mean. The batteries in some devices may be difficult or impossible to recharge or replace once deployed. Think about medical implants. You cannot do the surgery every time when the battery is depleted. It should also be noted that power consumption depends on many factors other than the algorithm used, such as the threshold voltage, the clock frequency, and the technology used for implementation, also the temperature and so on, right? So it is not that easy to measure, in other words. So let's focus on some metrics. Latency. Latency is especially relevant for certain real-time applications. For example, automotive applications where very fast response times for components such as steering, airbags, or brakes are required. So in today's autonomous vehicles and smart vehicles, actually each part of the car communicates with each other. So for instance, one of the tires may hit a rock and actually it may send this data to other parts of the car and tell them how to behave. So this has to be really fast. Okay. Latency can be defined as the measure of time between the initial request of an operation and producing the output. So in terms of cryptography, this is the time between you have the plain text and then obtain the ciphertext, right? Some algorithms maybe have a high throughput, but also have high latency. Our aim is to have low latency so that real-time applications can benefit from it. For example, the latency of an encryption operation is the time between the initial request for the encryption of a plain text and the reply that returns the corresponding ciphertext. So this is what we mean by latency, okay? So this is important because different types of algorithms have different latencies. For instance, think about a stream cipher. In the stream cipher, if we have initialization phase, it may take a lot of time, which would increase the latency. Then maybe you have a very high throughput, but you would have also high latency, right? This is why for some operations we prefer lightweight block ciphers when we need latency. Throughput. Throughput is the rate at which new outputs are produced. For example, authentication tags or ciphertexts, which are relevant for our course, since we are talking about lightweight cryptography. Unlike conventional algorithms, high throughput may not be a design goal in lightweight designs because maybe you're dealing with really small devices and they are not going to produce a lot of data, right? Maybe they're measuring something like the temperature, so the data is not that big, so you don't need much throughput. However, moderate throughput is still required in most applications. So let's move on to hardware-specific metrics. Resource requirements for hardware platforms are typically described in terms of gate area. The area of an implementation depends on the technology and the standard cell library and is measured in micrometer squares because it determines how, the area it requires on the hardware, right? Area can be stated in terms of logic blocks for field programmable gate arrays, FPGAs, or by gate equivalents for ASIC implementations. Okay, so of course all of this depends also, as mentioned here, on the technology and standard cell library. An implementation may require more gates in one technology and less in another one. So this is why it is hard to compare results in the literature because they may be measured in different technology, depending on the nanotechnology. So on FPGAs, a logic block is the basically configurable unit that contains a number of lookup tables, LUTs in short, flip-flops, and multiplexers. Logic blocks are implemented differently on different FPGAs. The number of LUT, flip-flops, and multiplexers depends on the FPGA family. The number of input and output bits of the LUTs also depend on the FPGA family. So as you can see, almost everything depends on the FPGA family. So it is really hard to compare this stuff. So if you're comparing two different implementations, you need to do it on the same FPGA to have a fair comparison, actually. So for instance, two different implementations having different number of LUTs may have same number of LUTs on a different FPGA. So you have to, check it on every device. For ASICs, one gate equivalent is equivalent to the area that is required by the two input NAND gates. The area in gate equivalence is obtained by dividing the area in micrometer square by the area of the NAND gate. The number of gate equivalents of a hardware implementation is therefore very specific to a particular technology, so that it is not possible to directly compare the number of gate equivalents of implementations across different technologies. So this is also done in the literature because somebody obtain an implementation and measure gate equivalents, for instance, saying that AES requires 3,500 gate equivalents. Then you design a different algorithm as block cipher and say that yours is better than AES because it requires 2,000 gate equivalents, but you are measuring your implementation on a different technology. So then actually it is not that fair to compare them, right? A low-cost RFID tag may have a total gate count of 1,000 to 10,000 gates. Okay, so think about smart cards. Maybe the smart card you have 10,000 gates. So at this point you might say that, okay, I can build design a big block cipher and maybe spend 8,000 gates. But don't forget that these gates will be used for other purposes too. So you don't have everything for cryptographic operations. Actually, you only have like 200 to 2,000 gate equivalents only for security purposes. Okay, so this is why you need small implementations. This is why in the past industry designed their own algorithms instead of putting AES inside their smart cards because they realized that they would need a lot of gates. Instead, they designed something simple, and this is why we can clone many smart cards. Okay, that is the summary of the story. When I say security purposes, actually meaning all of the cryptographic algorithms. So if you need a hash function and put SHA-256 there, then you also will be spending more gate equivalents, right? Area requirements and power consumption can be correlated, in which case minimizing area also tends to reduce the power consumption. This is actually an important physical phenomena, actually. This is actually why we are getting better GPUs every year. Okay, so think about the GPU. So it has a large size, right? But every GPU in the last years always have the same size, right? So you, for instance, buy a NVIDIA GPU with a name 3090, let's say. So assume that it has around 8,000 cores. So 1 year later, they produce another GPU, this time name it 4090. The size is the same, but now it has more cores. Because due to nanotechnology, now instead of putting 8,000 cores to the whole stuff, you can fit it in the smaller part of it. Now you have empty space. You put more cores there, and this time you have 16,000 cores for GPU 4090. But since you added more cores, you would expect to consume a lot more electricity, right? But since you made things smaller, they consume less energy. This is why we still have GPUs better and better every year, but they at most consume like 300 watts or something, okay? This is why area is also important. If you make it smaller, then your power consumption will be better, right? This is why you need a smaller algorithm at the end of the day. For software-specific metrics, for software applications, resource requirements can be measured by the number of registers, as well as the number of bytes of RAM and ROM that are required. Functions that use a small number of registers have a lower calling overhead, as fewer variables must be placed on the stack before the registers can be overwritten. This is really important. ROM is used to store the program code and can include fixed data, such as S-boxes or hard-coded RAM keys. Of course, this may also cause a security problem in the end. You have to be sure that nobody can access that ROM. While RAM is used to store intermediate values that can be used in computations, this can lead to additional trade-offs between calculating values on the fly versus looking up values in a table. Because if you're planning to looking at tables, you will be storing them at the ROM. But if you're going to calculate them on the fly, then you'll be using RAM. That is actually the difference.